So thanks everyone. I'm James. I'm an engineering student at the University of Surrey, and I'm here to do a talk on satellite communications, really. So this is kind of what I've learned in the last kind of year and a half of amateur radio, and my course content as well on radio and kind of the interesting things I found out there. So in orbit, there's a lot of satellites, which do all sorts of things, ranging from weather, communication, geolocation, scientific purposes, a lot of defense as well, the International Space Station, and pirates, which you may or may not know. So, which actually falls under the defense, because the US government released a lot of satellites in the 60s and 70s, which were just analog with kind of no authentication, and now they're used by Brazilian cartels to communicate freely and bouncing things off satellites, and there's nothing they can do to stop them, which is pretty interesting, if you ask me. So I'm going to jump right into digital video broadcast, which is a protocol that so it was designed for when you need to forward a video signal over a much larger area. So obviously digital TV came around in the 80s. We needed a way to get things through, and it's really a set of frequencies and ways to manipulate a signal, kind of FM, AM, things like that, and what you can do at different levels of noise. And over the years, it's been extended many times. In the 90s, it was extended to allow for audio calls, news bulletins, which were a thing apparently, fax, and then eventually Internet Protocol in 2003. And there's quite a lot of issues with having Internet Protocol over satellites in a kind of deep orbit, because it takes quite a long time for signals to get out there and get back. So you'd be looking at about 160 milliseconds of latency just to traverse that, which is ungameable, even on some of the most dated titles. So many what we say VSAT, which is kind of maritime and remote devices, where you need a connection to the internet, and there's no real way to get it there across land. So you use a satellite. It is a very high latency, very low bit rate, and when you add encryption, it adds a lot more latency, and there's not much you can do about that. So it's often disabled intentionally, or simply not built into modems, the system. So anyone who can receive the signals can view the traffic. One part I missed out there was the extensions for the extensions to the digital video broadcast protocol. So it all uses the original video heading. It has a lot of I guess you'd say tech debt. I don't know. Anyway, anyone who can receive the signals can view your internet traffic, which is not ideal. So this is this picture of what a geostationary satellite would look like, and its view of Earth. So it has a very large antenna pointing at a very large geographical region on the Earth, and it will have from the Earth. You'll have your users with very small points of presence, with a tiny rotating dish pointing right back at it. And what you'll notice is that it's a really wide beam. It's it's not focused in any way, and it's not going to and it's not going to discriminate against where information goes. So when it sends information back down to devices over the entire coverage area, which can sometimes be multiple continents, everyone gets the signal. And as we said, if you get the signal, you have the traffic. And there's a lot of interesting traffic you can find coming down from maritime ships, because they often run email servers, unencrypted web portals. You can see a lot of requests going into those systems, but you can't see them coming back, because if you remember, the signals going back are very narrow, and they're just coming straight back from the Earth to the satellite, because they're all directed. As promised, these are the things which you need to understand on building a ground station. So satellite dishes, they are parabolic dishes which magnify a signal to a point, and that point, which is usually a spherical thing, the thing on the front of the dish with the arm hanging in front of it. It's what we call a down converter, which will take the very high frequency that's been focused and centered on the down converter and convert it to a frequency which can actually move through the wire. Otherwise, you'd face what we call very high reactive losses. The caveat of having that down conversion is it needs power, though. So we have a thing which we call a bias T, which enables the down conversion to take place, and then you will have that part of radio spectrum coming through your coax cable, or whatever setup you have to receive that. And coax cable is another word for wire, but I'm not sure why I put that in. So SDR, I'm sure some people will be familiar with it. It's a software-defined radio, and what it lets you do is it takes an analog signal, radio frequency signal, and translates it into the digital domain. So if you have any experience with kind of electronics, it would be like it's basically a souped-up analog to digital converter, because you're taking an input signal and converting it into a known number of bits. And then obviously software, which are kind of just zeros and ones. It's pretty comprehensive. And there's some brilliant software out there for dealing with radio signals, for finding things. And yeah, so those are the kind of the key elements you need to make a ground station. And so onto some options for SDRs. So there's the budget choice, which is RTL SDR, and I'm sure quite a few people will have used that before. It's very cheap. You can get one for about 25 quid. I know they released a new generation recently, which is at least a bit better. But it has a quite narrow bandwidth. So if you imagine you're looking at every possible signal which you could see on the radio spectrum, so you see kind of broadcast radio like Radio 4, you see some airband traffic after that, and going all the way up to kind of seeing your car keys send data at about 400 megahertz. You'd only be able to see very small slices of that with an RTL SDR. A big step up is HackRF, which I know a lot of people have heard of. It's mentioned a lot at talks in Black Hat and such like, and it's used extensively for research. It is quite expensive. It's the cheapest knockoff you can get is about £160, and but it has the advantages of being quite high bandwidth, so you can see a really large chunk of radio spectrum at the time. Quite a low noise floor, which means that you can pick out weaker signals, which you couldn't do on the RTL SDR. And then finally the Pluto, which you can get for about £300. It has reasonable bandwidth, but the most important thing about it is that it can receive and transmit at the same time. So if you wanted to kind of prototype a communication system, do kind of a meaningful work on with satellites, so sending and receiving data, especially with more modern systems, you'd really want one of those. So that takes us back to kind of spying on the maritime internet. So you can see all of the traffic coming back on a satellite to ships all across kind of your continental area. And one interesting thing which you can do is they often have quite poorly configured routers on them, and it's usually very old equipment. And sometimes you'll find that they use globally routable IP addresses directly. So you'll just see traffic going addressed to a globally routable IP address that is destined for a ship. And they do this mostly because they think that putting mail servers on ships is a brilliant idea, which, it has a few advantages, but it is one of the main reasons which the post office protocol exists, if anyone remembers that, which is the alternative to IMAP. So one interesting thing which you can do with that is once you find an IP address which is of a ship, if you send any data to that, you can then receive that anywhere in that area. So it's kind of like you could have a information leak that you're just collecting with a satellite dish in your back garden, and if it was traced back to the IP source, all you'd be able to say is that it was somewhere in Europe or North America, which isn't quite a large search area. So that's kind of the summary. And what I wanted to move into on this was kind of the amateur satellite radio, which is so you're legally able to transmit to satellites using it. On things like the ISS, they actually have an amateur radio repeater, and there is no better place to learn information about antennas, propagation, signal hunting, and every part of making a radio system which you could imagine. So in these images, this is the satellite which we built with the Ear Society at university. We commandeered a roof and built it there. You can see Guildford Cathedral in the background, which has blocked our view to satellites numerous times. And on the right there, on the left, in the right picture, is our Radio Shack. So that's our very big antenna. That's for kind of terrestrial use. And then on the other side of that image, you see a massive satellite dish, which is not ours. It belongs to the Space Center, and they won't let us use it, which is why we built our own dish there. Anyway, thank you very much for listening to my talk, and I hope you learned something and potentially continue your interest in satellite internet.